Okay, for those of you who have, since you've been working with exponential functions, had a problem with the fact that we can't actually solve certain equations involving exponents, you've kind of just been told to guess and check about that, you might not love that. So today, we are actually going to learn how we can reverse the process of raising something to a variable exponent. So we're going to learn a technique that's going to allow us to solve questions like 6,000 equals a to the power of x and be able to work out what is x when a is 4. And the cool thing is we can do it in a way where you don't have to guess and check. So what if our exponent is actually like a decimal or a fraction? We can actually work that out exactly. And it's using a really cool function called a logarithm. Okay, so what is a logarithm? Okay, logarithmic functions are inverses of exponential functions. So as we did in the transformations unit, we're going to be looking at an inverse function. So logarithmic functions are inverses of exponentials. Okay, so how do they work? So what we do is when we're talking about a log, just like with an exponent, we have a base. So we would say the log base b of x equals y. Okay, so this is what we call the base of the exponent, of the logarithm. And what a logarithm does is it unexponents something. It tells you what exponent it has. So log is short for logarithm. So we would say, for example, log base 2 of 8. So what that's asking, log base 2 of 8, is what power do I have to raise the base to? What power do I raise the base to get in order to get 8? Okay, so that's what this logarithm question is asking. And the answer is, well, if I raise 2 to the third power, I get 8. So the log base 2 of 8 is equal to 3 because 2 to the third equals 8. Well, let's look at another one. What if I wanted to do log base 10 of 100? Log base 10 of 100 equals 2 because 10 to the power of 2 equals 100. Okay, so it's asking you what power do I have to raise the base to get the number I'm taking the log of? Well, that's all well and good, Miss Eaton, but first of all, it still feels a little bit like guessing and checking. So how are we going to get around that? Well, first let's take a look. We can actually graph these functions. So we can use these to estimate different values even if we don't have an exact answer. So if you remember what an exponential function looks like, and I'm just going to kind of draw it in, it looks like this. Because we have an inverse function, this is going to be our exponential function reflected over the line y equals x. So where our basic exponential function had a horizontal asymptote, our basic logarithmic function is going to have a vertical asymptote. Where our exponential function had the special point 0, 1, our logarithmic function is going to have the special point 1, 0 if it hasn't been transformed. Where our exponential function had the point 1, b, our logarithmic function is going to have the point b, 1, just with the x's and y's switched. So we get here, this is a graph of y equals log base b of x with no transformation. And if we want to look at it algebraically, what that means is our x values are equal to b, whatever our base is, to the power of y. So how can we convert? The easiest way to start working with logarithms is just to think of them in exponential form. We're really used to thinking about exponential expressions and equations, but logarithms are an entirely new function. So we're going to look at log base b of x equals y, and we're going to think about how that goes into exponential form. So the base of our logarithm is the base of the exponent. What it's equal to is the power of the base. And what you're taking the logarithm of is what your power expression is equal to, what your exponential expression is equal to. So we can think of having these two little arrows that cross. So our y is going to the other side to become the exponent, and then what's inside the logarithmic function, the x, is going to be what that exponential expression is equal to. Let's do a few examples so you get the hang of it. And generally, what we want to do as we're starting to understand, the most important thing is we're starting to deal with logarithms, is just to be able to think it back into exponential form. We'll talk later in the course, getting into the next couple sections, about how we can actually use the scientific calculator to calculate those exact values where we have a decimal or a fractional exponent. So we have log base 3 of 81 equals x. So when I look at a logarithmic question, the first thing I want to know is, what's it asking me? Well, if I rewrite it in exponential form, I know that 3, my x comes over here to the power of x, my 81 is going to go to the other side of the equal sign, equals 81. So it's just asking me, what power do I have to raise 3 to get 81? And 3 to the 3 squared is 9, 3 to the third is 27, 3 to the fourth is 81. So here we have x equals 4. Okay, so let's take a look at log base 5 of x equals 4. So what's this question really asking me? So I want to raise the exponent. There's some number that when I take the log base 5 of it, I get 4, which means that 5 to the power of 4 is going to give me what my x is. So all I have to do is raise 5 to the power of 4, and I get 625. Okay, so now I'm going to look at log base x of 256 equals 4. I get x to the power of 4 equals 256. Well, I know how to solve an equation that has a variable for a base and an exponent. I'm just going to take the plus and minus fourth roots of both sides. Okay, and so I get x equals the fourth root of 256, and if I throw that into a calculator, I'm going to get x equals 4. Okay. Why am I throwing away that positive and negative square root? Let's go up and look at our logarithmic function. Okay, if we have a b here, we notice that our b is giving us a positive x. We can't actually use a logarithm with a negative base. And so for our one of the restrictions on our logarithmic function is that we have to have that the base, okay, base must be greater than 0. Okay. So one more example. We have log base 9 of 1/3 equals x. So that question is asking us 9 to what power is equal to 1/3? Well, we're actually going to have to, well, I want to take the square root of 9. Okay, we have to recall square root of 9 is 9 to the 1/2. Okay, we also have to recall that 1 over 9 is 9 to the negative 1. So if I want to reciprocate something, it's a negative exponent, and if I want to root it, it's a fractional exponent with that root as my denominator. So we actually know here that 9 to the negative 1/2 equals 1/3. So x equals minus 1/2. And that's the power that we are looking for. Okay. So if we're going to graph a logarithmic function, because a logarithm is a function just like all those other functions we've been working with, we have our basic logarithmic function that we looked at. Okay, and we're going to actually start with maybe a logarithm base 2. So let's say we have a y equals log base 2 of x. So we cross here at 0, 1. We're going to have our next point up here at 2, 1, and it's kind of like that reflected exponential function. So what are the features we have? Well, remember our horizontal asymptote for the exponent turned into a vertical asymptote. So we have a vertical asymptote at x equals 0. So that's where our vertical asymptote, if we don't change the location, is going to be found. We also are going to notice that we have, and that's really the key thing. Once you find that vertical asymptote, you can just plug points into your equation and generate a table that you can use. You just want to know that you're starting at the right place with that vertical asymptote. Okay. We also have that special 1, 0 point and that 2, 1. We have to think a bit about the domain. So remember, we had a range restriction with our exponential function. Usually it was going to be y greater than 0, and it's before it's been transformed. So here we have a domain, and the domain is that x is strictly greater than 0. It doesn't ever reach 0 because it has that asymptote. Y for our logarithm is unrestricted. It can get as small or as big as you want, but x's always have to be positive. So you can't take, this is going to be a rule that we use as we get into logarithmic equations later, is that you can't take the log of a negative number. So when we write a transform logarithmic, so we have our transformations, on our logarithmic functions. We have y equals a log base b of x minus c plus d. We can have a reflection in either direction. So this, if we have a negative inside the function, that would give us a reflection in the over the y-axis in the x direction. If we have a reflection outside, that would give us a reflection in the y direction. So let's say we wanted to graph the transform function y equals negative log base 2. We're going to use our log base 2 function that we have over here of x minus 1 and then plus 2. Okay, so we're going to check our function. So this is a reflection in x-axis because it's outside the function. This is a translate 1 unit right, and this is a translate 2 units up. So generally when I'm doing these kinds of transformations, I like to do it in state. If I'm going to just transform from the function I'm given, I like to do it in a couple steps. So first thing, I'm just going to do the reflection. So I've got here, this is my 1, 0, it's going to be the same, and then I'm going to have just a 2, negative 1 point here. Now I'm going to translate 1 unit right. So my asymptote is going to move 1 over. Everything is going to move 1 over, and then I'm going to translate 2 units up. So I have this point here is going to go over 1 and up 2, so it's going to be here. Then this point is going to go over 1 again and up 1, 2, so it's going to be up here. So my transformed function is going to, whoops, doing the wrong points here. We're going to do, this point is going to go over 1 and up 2, so it'll be right here. and this point is going to go over 1, and, sorry, this point is going to go over 1 and up 2, so it'll be right here. So we've got this new function that's coming down right here. And that is what our transformed logarithm will look like.